I think we finished discussing all these things. Slow start. A couple of things I might have missed with some of you, like when you have a retransmit, you identify the missing packets based on duplicate acknowledgements. The same acknowledgement, I mean the acknowledgement packet with the same acknowledgement number is transmitted multiple times. So these are called duplicate ACK. I mean we explained it, but it is also called dup ACK, as you can see there, duplicate ACK or dup ACK or dup ACK in short. Okay, so you may come across this term in future. So I just wanted to mention. And the point is that in the case of voice, which is a very common application, the data packets are generated every 20 milliseconds. This is the standard for usual digital communication systems. And say from 2G, 3G, always it has been the case. Data packets are generated, and this is called vocoder. A an encoding action works along with the voice input part of the circuit, and finally it generates voice packets. So even if you look at the 2G technologies, I said that 4.615 milliseconds is the time frame, right? So every 4 of them contain one such voice packet, which is almost 20 milliseconds. So similarly, other technologies also take care of the voice packets. Now, these voice packets in the case of IP, or it usually takes up 30 bytes. So when you add IP and TCP headers, there are 40 bytes additional header. If you use CS, then you don't have these headers. But with the IP option, when you use VoLTE, IP routing, then you are adding this 40 bytes of header, which is too much. I wrote it somewhere. Yeah. So for VIP packets, this is too much. For the control overhead is too much compared to your actual data payload. So, but you need to send them these packets because you cannot just accumulate a number of packets and then send, creating a large IP packet. You cannot send because then the reception quality won't be comfortable. You need to have continuous arrival of all these packets and reproduction of the sound. So there is some to increase the efficiency, some header compression is used. Header compression can also be used for other applications, but voice invariably uses this header compression, which reduces the header bytes. And in my book, I explained this header compression technique. There are actually few techniques, but anyway, I explained this header compression in my book in detail. It can reduce it's just create some negotiation, and the header bytes can be reduced from 40, it can be reduced to only 8. Anyway, we were almost at the end, and these are few options. I said that see, fast recovery, fast retransmit, slow start, So it's up to you what you use in your particular TCP. Uh, TCP has come up with quite a few different versions. The earliest one did not have any of these three techniques, and it was called TCP Vegas. And these two are then popular TCP version, TCP Tahoe and Reno. Now what we have in Windows and Linux. Windows, the early Windows used to use TCP Reno. In the case of TCP Reno, you have both fast retransmit and fast recovery. And the number of DUPAC when you use fast retransmit is also 3, as we used in our explanation. And there is some modification of Reno. It's called new Reno. So this is what Windows used to use, but current Windows use little more complicated TCP, where you have two TCP flows, two separate, not flow, but two separate congestion windows maintained simultaneously. So little more complicated. Linux uses some other versions. Earlier it was TCP big. Now it is the one they use currently is TCP cubic, but optionally you can have TCP BBR. Depending on this, also depends on the packet error rate or packet loss rate. So what can be more appropriate for your case? But as I say that there are eh, almost a dozen or probably even more TCP versions available. Any questions? Now we'd like to discuss the variants of IP and TCP when you have wireless link. Only the wireless link does not necessitate the variant of IP. It's not a variant, it's a special way you handle the IP addresses. Uh, but if your wireless link also includes mobility, without wireless link, the mobility is not possible. But say for mobile phone, I mean, when by mobility we mean, I probably told you before that there are three different categories. Static, when you have a fixed location for your wireless service, and nomadic, which is like the example is Akash. You establish a wireless connection somewhere, but it is portable. It is possible for you to move it and then install it somewhere else. But that will be a new installation, taking some time and hassle. The third option is mobility. And oftentimes the term seamless is also used with mobility uh, to ensure that it is completely mobile. Okay. There may be some limitations in the mobility in some applications, but seamless means what we enjoy in our wireless phones. You don't feel any difference. You just keep moving, and everywhere it sustains the service. So for this kind of mobility, the ordinary way of IP use poses some problem. Okay, as I said that, let's assume that you this mobile node means the user who is using IP, who is connected to the network and using IP, but he can move. And by S, I mean someone who is connected to that, who is sending packets to the mobile node. So if uh, you are located here,
Sir,
then yeah, yes,
sir,
yeah,
sir, are you
yes.
sharing your screen?
Oh,
Sir, it's not visible.
sorry, sorry. I was sharing. Give me a second. Okay, I'm sorry, but is it visible now?
Yes, sir.
IP with mobility support.
Yes, sir.
Okay, so there is even a blue node, which is a user who can move, and this S marked blue node is someone who is sending packet to the blue node to Amen. Now, everyone is must be connected to a router, and they will be allocated some IP addresses. The problem is that you need some topologically correct IP address, meaning that when you will be allocated an IP address, it comes from a pool, and these pools are all managed based on the geographical location. In some other area, another range of IP address can be used depending on how the IP addresses have been managed around the world. So, like that some postal system that packets have to be forwarded and taken to a particular geographical location. So every geographical location uh, has a particular range of address, and that is the topology, the network according network topology you are getting this range. If you move to another location, then you go beyond the range that the say the router 2 has a range of IP address, a pool of IP addresses that it can allocate. But if you move far and you go under the service of router 3, then router 3 cannot allocate the same, the cannot keep using the same IP address. It has a different range of IP address. That means your IP address needs to be changed. But if you change your IP address, the sender needs to know. The sender will be putting your IP address on the IP packet when he forwards something to you. And accordingly, the packet will get to you. So if you change your IP address, that packet will not reach you. So this is a problem with mobility. You cannot keep the same IP address because you are changing locations geographically. But you need somehow to receive a packet from the same, I mean, uh, with some identity. So, like say, if you are changing your location, but the postal system is not updated, then you cannot get your letter. So this is a problem with mobility, and we'll now see how it is taken care of. It is uh, something
Sir,
called mobile IP is used. Yeah, yeah. Please go ahead.
sir, aren't IP addresses supposed to be unique? Then why does it need to change?
Well, because you will be allocated IP address by your provider. They'll use some protocol like they can use DHCP uh, to allocate an IP address. They can allocate you a static IP address, or it may be meaning that you have, when you configure your with a static IP address, uh, you will, like if you say work somewhere, when, when you, after you graduate, you work somewhere, so you'll have a workstation. Every day you have the same office and you work there. So most, it may happen, I mean, it depends on how they configure, but you may be allocated a fixed IP address. When I mean, they configure the internet connection on your computer, they'll allocate a fixed IP address. And the administrator will actually then knows who has what IP address. For every user, for every employee, they have a list of IP addresses. So this is called a static IP address. Alternatively, you can dynamically be allocated an IP address. Whenever you connect to internet, it will use some dynamic protocol called DHCP, which allocates an IP address to you. So either way, you have an IP address which comes from your provider, but he gets, how does it get allocated? He actually gets an IP address when he purchases the internet bandwidth from his provider, his upper layer provider. We have different tiers, like he may be taking service from a tier 3 ISP and tier 3 ISP from a tier 2 ISP. But whenever someone gets uh, internet connection, it purchases, he gets two things I told you before. First one is some bandwidth that you can use this much capacity to route your data. Secondly, you have you get a range of IP addresses or a pool of IP addresses, which it can allocate to you, to its clients or whoever is connected to this ISP. And since the IP addresses are managed with geographical distribution, like the postal addresses, someone else at a different location, ISP at a different location, will definitely have a different range. Okay, and I told you that from the IP addresses, people can actually recognize from, I mean, from where a particular packets packet is coming. So if you are moving far, then you'll go beyond the range of router 2. You're connected to a different router, a different, I mean, provider there. I mean, it may be the same provider, but with a different geographical location. If it is far enough, then he cannot maintain the same range. He needs, it will have router 3 has a different range of IP addresses. So when you are moving, you must be connected to a different router or different provider. So you get a different IP address. You must have it. Your IP address needs to be changed. Is it clear now?
Yes, sir. Thank you.
Okay. But with IP address, packets are routed. So you then miss the IP, right? So the solution in the case of IP version 4 is called mobile IP. And in the case of IP version 6, it is done in a simpler way, and it uses something called binding. So let us explain mobile IP first, because IP version 4 is still widespread. In this case, something called encapsulation, IP in IP encapsulation is used. You add another IP header. The lower one was the actual IP packet with some blue header, and you are putting that in another. This whole thing is taken as a payload, and a new IP header is added. So this is called IP in IP encapsulation. Now note that there are different terms: HA, COA, CN, MN. What are they? Well, By MN, I mean the user who is moving, mobile node. Now, originally, it was connected to some, when it first registered, some IP address was allocated by some router or network. So this is called home agent. That is like its home address. But as it is moving, it gets under the service of a different router or different network. And that we are calling foreign agent. And I mean, the concept was like that it may come back to the original, I mean, the first location where it registered first. So that is considered like home. And wherever you are moving, you may be moving to different places. All these routers or networks you are connecting to are called foreign agent. Now, as you are moving, you are under a foreign agent, you'll be given a different address, IP address. That IP address we are calling care of address, COA, care of address. And by corresponding node or CN, we mean the guy who is sending you the packets. I mean, within the network, somebody may be sending you packets, and that has to reach you. So that sender is called here correspondent node. Okay. Now the way it is taken care of, that you have moved from 2 to, you are under this home network in the beginning, but later you moved here, and currently you are under this foreign network. You are under this FA. This sender correspondent node doesn't know that you are moving, so it has the same IP address as you had originally under home, under HA, under home agent. Okay. So the corresponding nodes put that IP address. So it first goes to the router of home agent, and the router will forward you the packet. So the original IP address is used. But then the home agent does those IP in IP. Well, it uses, I mean, in the place of source address, it puts its own address, the IP address of the home agent. See, in the case of source IP, it was originally IP address of the CN, and destination address, it was IP address of MN. That's what it should be. But now, a new IP header is added with the source address of the home agent, and the destination address care of address of MN, current IP address of MN. So then the home agent forwards the packet, and the routers will be forwarding the packet following the care of address. So it will get to the router of foreign network, and the router will forward you the packet. So it gets to you correctly. Okay. So this is called mobile IP. This is the way it is handled. However, when you are sending back a packet to the corresponding node, typically it's a bidirectional communication. Even if it is not bidirectional, at the application level, there will be some packets to be forwarded, or even for TCP, when you are sending an acknowledgement, it has to be taken back to the sender, right? So as you are communicating, you're receiving your TCP packets, you are also sending acknowledgement. So there is always some bidirectional flow. If there is, at the application level, if the data flow is unidirectional, then the data in the reverse direction will be only for control purposes. So that data will be very slim. The data will be very slim there. Only a few packets may be coming back, but there will be some packets anyway. So when you send some packets in the reverse direction, you don't need to use any difference. Now it is all fine, because you must know the correspondent. Once you get to you have to decapsulate. It is encapsulated, and in decapsulate, you remove the this additional header and start reading this IP header. So you know who has sent you the packet. You know the IP address of the corresponding node. So when you send any packet to him, you just use that, the address of the corresponding node in the destination address and your own IP address. This IP address is not what you had originally under HA, rather what you currently have under AP. So this is what you use. Okay, importantly, the source address, when you say you're sending a packet back to a CN, is what you currently have. The care of address is your source address. So this is called reverse tunneling, that you are sending a packet back to the corresponding node. The corresponding node is, in this case, we're assuming that the corresponding node is not moving. If it moves, then you need again the same kind of approach for reverse packets. But if it is not moving, then you can put the destination, you can put the corresponding node address in the destination address field. But since you are using your current address as the source address, you have in the system the topologically correct address. Based on your location, whatever your source address should be. So you'll not be blocked by some network security. There can be some firewalls, network security at your premise to block anything insecure. Okay, so if you have something suspicious, it will be blocked by the firewalls. So since you were using care of address as the source address, the packet shouldn't be blocked. Okay, but there is a problem that it takes longer for the packet to get to the receiver. It first goes to the home agent, then encapsulated, and then forwarded. So it takes a longer route, which may be sometimes much longer. So it will take very long time to get to the receiver. So a solution to that is what is called triangular routing. So this can be used sometimes. Okay, it routes directly to the foreign agent. Well, instead of sending via home agent, in this case, the home agent needs to send the care of address. Okay, the current IP address of the mobile node to the corresponding node. The original sender will be updated with the current IP address of the mobile node. The home agent will be doing that. The home agent informs the original sender, the corresponding node, that this is currently the IP address, which is not easy always. But if it is done, then it is called triangular routing, and then you have some saving on time. Okay. So this is pretty much what I wanted to cover. Just one last thing. If we just give me a second, please. Sorry. Is it visible? Is the slide visible?
Yes, sir.
Okay. Well, as you are moving, there can be, changes of base station. You are going under the service of a different base station. and say you are going under a different router. So this requires some handover, and in some cases, this handover causes some data packet losses. I mean, as you are changing the foreign agent, you may move to another location and go under the service of another foreign agent, another router. So this takes a while. The switchover can take a while. You are getting disconnected from this FA, and then a new connection is established with the new FA. During this transfer procedure, the packets would still, the corresponding node doesn't know that you have a temporary disruption of connection. It will keep sending the packets. Now, to avoid any packet losses, the FA keeps storing or buffering these packets. Once you are connected to a new FA, these packets are forwarded. I mean, from the old FA, the packets are forwarded to the new FA. And once you're connected to the new FA will be sending you the packets. So this can be done when the packet losses are avoided, but it is not always necessary. Okay, I mean, it's not. I mean, the packet. I mean, errors are not always a critical problem. If it is a critical problem, then this measure needs to be taken. Now, this slide I'll not go through. I'll skip it. I just included it in the class notes because it explains the different steps. We are just discussing the basic concept of mobile IP, but there are a lot of details. So at least the actions required there. Okay, there are some advertisement messages. There are exchange of a few messages which help the whole things work. So here, I mean, these major actions are listed. So I included in my slide, but I'll not go through it. For IPv6, the procedure is simpler. In this case, it is basically just like triangular routing. Whatever we had here, triangular routing is used, but with a different name. The concept is the same. Almost similarly, it is implemented, but it is called something. It is called binding, and for a particular period, this I mean, I said that in the case of triangular routing, the home agent must inform the sending side, the corresponding node, the current address of the mobile node. So this is exactly what is done. So this is how where you was registered, but when you are moving to network C, sorry, the corresponding node is under network C, and you have moved from network A to network B. Network A is so there is some registration. I mean, basically, the the there is a negotiation between the mobile node and the corresponding node, and this negotiation has some lifetime. It's called lease time. It tells you, the mobile node tells the corresponding node what its current address is. So the corresponding node can just send the package to that address. This is called binding update. The corresponding, the mobile node gives you with a binding update message. It is called binding update message. Gives you the current address. But since it is for a particular list time, as the list time is going to expire, the corresponding node sends a request that it is called request binding update. Okay, then the mobile node again the new gives the IP address, which may be the same or it may be something new currently. So once in a while, you have to update the address because the care of address may change. The corresponding node sends a binding update request, and then the mobile node sends the binding update message. Okay, with the current IP address information. Okay, and okay, so there is also, with the home agent, this negotiation is taken place. Okay, then uh, the home agent tells that with whom it needs to do the binding update operation. Okay, so this is how it is. So in IPv.
Sir, you are not audible.
Oh, I'm sorry. I was disconnected for a while, and then the microphone got muted. Uh, so I think we completed before getting muted. I think we had completed the whole mobile IP. Okay. In the case of IP version 6, it is at the last. I was just saying that in the case of IP version 6, by default, you have direct data transfer. What you use with the triangular routing option for IP version 4. In IP version 4, the default is that you send the packets via home agent. But optionally, there can be negotiation and there can be triangular routing when you can have direct data transfer. On the other hand, in the case of IP version 6, there is no routing via home agent. It is always direct routing, just like triangular routing. So the negotiation is taken place and then they route directly. Okay, so which is called binding or binding update. Any questions? Do you have any questions? Now we're gonna discuss the variations required for TCP when you have a wireless link. Do you see the slide? TCP with wireless link.
Yes.
Yes, sir.
Yes, sir.
Okay, both IP and TCP are now pretty old technologies. I mean, they started with the inception of is internet, but it has been, quite a few decades already. And both TCP and IP were originally developed with wired network in mind. In those days, it was all wired network. Well, there were very few wireless connections, and the wireless connectivity was very limited. The protocols were developed with only wired network in mind, and they could also run when you have any wireless link, but not perfectly. Over time, the number of wireless links or the wireless uses has grown too much, and the inefficiency with the wireless link now needs to be resolved. So, like IP, I mean, once again, for IP, you don't need those mobile IP just when you have a wireless link. You need that only when the wireless link comes with mobility. But in the case of TCP, if you have a wireless link, you may need it. Uh, it may be a requirement, whether you have any mobility or not. However, if you have a very good quality of wireless link, then the original TCP can still, it may not be. But in most cases, wireless link comes with some poor uh, data transfer quality. That poses a problem with TCP, as we're going to explain now. So the original TCP needed some changes, maybe say a couple of decades ago. People started changing, uh, started adopting some variations of TCP when there is a wireless link. See what problems. Well, the TCP uses some congestion window to adjust to adapt to the network capacity. And it assumes that whenever there is a missing of acknowledgement, you have, or a timeout expires, you get duplex retransmit. You have a you have some network congestion. Some routers on the way are uh, overflowing. So it then reduces the data rate. But in the case of wireless link, very commonly the reason is something different. With wired network, packet drops or packet losses are very, due to errors, due to poor link, the packet losses, the packet cannot be detected correctly. These are very rare options. But if it is wireless link, then it is more likely that a packet has been dropped because of poor link on the wireless link instead of any network congestion. So the reason is deep. And once you survive temporarily, just there can be some sudden interference which causes like burst error. I'll tell you why. Say in the mobile, well, have you been demonstrated anything on the spectrum analyzer in the lab class? The spectrum analyzer, is it demonstrated in the lab class? Guys?
Yes, sir.
Yes, okay. So did they uh, show like say this set up a call using a mobile phone around the spectrum analyzer and then you see did you see this kind of things?
Yes, sir.
You, hmm?
Yes, sir.
You see, yes. So it happens when you first make a call. I probably told you that it's all power control. The power control, how much power you can use for transmission.
is under very, uh, frequent control. But when you first transmit something, when you're first setting up a call, you first knock the network. You send a bit at the first place. There is no prior command from the network that use this much power. You don't know. In this case, it uses pretty high power and wait for response. If there is no timely response from the network, it increases further the power level. So you see some sudden spikes. So there can be some reasons when you use suddenly high power, and in these cases, it's all fine for you, but you are interfering somewhere else in some cells who is using the same frequency. So there can be sudden interference, maybe generated by your own system, especially cellular network. Suddenly you can get it, but this is very temporary. It's just a spike. Once the network hears you, it sends a response and tells you that okay, control your power. Okay. Like sometimes in our country, suddenly we see that people are quarreling, and then some okay, and people may shout. Okay, suddenly people may shout, and then the other side may respond. Okay, he may request to keep his voice low. So similarly, you can suddenly use high power, especially when you make a call. But the network immediately tells you that how much the power should be lowered, should be the appropriate power level. So in the system, there can be sudden interferences or there can be sudden noise also. So that causes the reception quality, uh, suddenly hampered, and some packets are in error. So this is called burst errors. And when there is a burst error, readily it would recover because the power is already take control by the network command. So it is over. The link is now link has started working fine. But with TCP, the TCP sender assumes that some packets are lost, so it must be network condition. It reduces the power, and we know how it throttles. It may bring the congestion window to one packet size. So but your link has recovered. It is now working fine. So just for no reason, the data transfer would go inefficient. So that can be a severe problem. Try to get the point. Why we have this new requirement? If it is a word error, then you cannot have this kind of sudden interference. Your words are all protected. Interference cannot get inside. But when you're using a wireless link, the whole the TCP connection may be from USA up to your mobile device. So it's a long connection with so many hops on the way. But this last mile is a wireless link, which is causing an issue. All the way a TCP connection is maintained. It's an end-to-end connection. The sender may be located in a different continent, is sending you something. A protocol, TCP is end-to-end connection protocol. A protocol is used, and we know how it is done. So all the way the network is fine. At the end, your wireless link had a problem, but that was very temporary. It has been recovered, but the sending side doesn't understand. It assumes that the network has got congested. So in the case of wired network, if it was all the way wired, you would not have this problem. But whenever there is a single wireless link, you get this kind of, especially with non-LOS connection. There can be some wireless link LOS connection. The base station is connected to the core network, setting up LOS connection. That may not cause this kind of problems either. Anyway, so you see that unnecessarily it reduces the congestion window and the throughput or the data it suffers. And the point, this one happens when you have mobility. If you don't have mobility, the first point is more important, but this is, this is also important, but in this case, uh, uh, it happens when you have mobility. You're moving, then you may move to another base station, then you have suddenly you have to break the connection with the old one and set up a new connection. It may not be always the case, but there can be in 3G they use soft handover. The connections are retained. But it may be the case that you have a temporary disruption. You're not connected temporarily. But after a while, you have a new connection with the new base station and then you recover again. But again, the sending side assumes that, oh, the network has got congested because some packets are lost. This packets could not get to the receiver, it could not get the acknowledgements correctly. So there must be congestion on the way. So I should reduce the data rate. No, you shouldn't. The network, it was a temporary disconnection or disruption, which is recovered once you establish connection with the new base station, once the handover is complete. So if you reduce the congestion window should change when there is a congestion in the network. There is no congestion, but it is still reduces the congestion window, and again you suffer from poor throughput. So this is why the normal TCP is not efficient when you have a wireless link. Rather, some variants have been proposed and they're in use. Uh, I have listed here the major variants, and the third one, mobile TCP, is probably the most popular one. And the first three are all major solutions or popular solutions: ITCP, Snow Protocol, and mobile TCP. The fourth one is unpopular, though. Okay, so we'll briefly explain them now. Well, the there is something called split connection approach. This is used in some of those variants. Well, we understand that TCP is an end-to-end connection, and a part of this whole connection, which is a small part, just you are connected to the base station all the way up to the USA. So many hops you have in routers, all these connections are wired, so they are not, they don't need any special attention. But this last mile wireless connection is requiring something different for TCP. So in a split connection approach, the TCP is broken. Instead of using end-to-end, it's called semantics. Instead of using end-to-end semantic, it is just broken into two parts. So there will be two TCP connection up to the base station. Up to the base station, you have, so the other end we assume fixed. It has a fixed location. So the fixed location, fixed host up to the base station, you have some TCP connection. And you have another TCP connection between the over the wireless link. Okay, so there you just use a TCP connection according to your need. Whatever. Configure your TCP based on this and this. So two TCP connections are used. So this is what can be done. This, if you use that, it is called a split connection approach. Now, in the case of ITCP, this split connection is used. Both Snoop and ITCP, the first two variants, you use split connection approach, but little differently. So in this case, the it is just retransmitted, or it is actually just the simple version. Simple version. You just use two separate TCP connections and configure them according to your necessity. In the case of Snoop protocol, you buffer the packets at the base station, and because you know that this is the wireless link will have a
Sir,
temporary shutdown. Yeah. Yes.
sir, can you please repeat the
Yeah. Well,
ITCP portion
yeah,
again?
that the difference between ITCP and Snoop protocol. Okay. Very briefly, I'll explain this for variants. For the mobile TCP, which is most important here, I'll spend quite a bit of time, but the rest three I'll go through very quickly. See, the split connection can help you, I said, if you separate the TCP. Instead of end-to-end, you use two separate TCP connections and configure them accordingly. So if you just separate and use in an ordinary way, it is called indirect TCP or ITCP. But if you if in the case of Snoop protocol, the base station buffers the packets. Well, that because it knows that the wireless link gets some temporary shutdown, which can be recovered quickly. So base station rather buffers. So it is not done at the TCP layer. Rather, some lower layers are used for this buffering. You see, it is done in a lower layer, and the buffer packets are then retransmitted over the TCP. So you get when you are getting two packs, okay, you already have the packets. I mean, on the wireless link. On the wireless link, the base station is getting a dupe, so meaning that you have, I mean, it's an indication that some is a drop. So once you get sufficient number of duplex, you have the time to retransfer. But those packets are already buffered. You don't need to, I mean, bring it from the sending side. You have the packets already buffered. So whichever packets you cannot forward now, you buffer them at the base station. And once the wireless link recovers the temporary issues, you just retransmit. So this is this is better. You can more efficiently, or you can handle the problem faster. Okay. So, but if you don't buffer, then it is ITCP. Now, both this ITCP and Snoop protocol come with an issue that in the case of handover, for we had two reasons, like the radio link quality can suddenly be very poor, or it can be even almost nil, okay, which we consider, we in common speech we say out of coverage. Okay. Or there is also another term, radio link failure. So the radio link can fail, RLF or radio link failure. Maybe I write down the term RLF, radio link failure. And sometimes we say out of coverage. Or the signal quality is too low to sustain any service. So in those cases, it's all right. But no, sorry, I put it this way. I mean, when you have the I mean, out of coverage period for, I mean, disconnection period for a significant time. It may be because of handover, or maybe those RLF, temporary loss of copper. But if it is for a significant time, if it takes for you, it recovers, but it takes a while for you to recover. Then you see that the base station has to buffer too much data. Or if you think about the foreign agent, see, when we discussed mobile IP, we mentioned that when you change the FA, you can, buffer the data in the FA and then forward. So anywhere you buffer the packets, there will be too much buffering if it is for significant period, and then you have to forward it. So huge data may needs to be forwarded. Huge data may needs to be buffered at the base station. I will change the language little bit. It may be buffered at different points, but wherever you do that, for a significant time of outage, the buffering will be too much. Okay, the buffering requirement is too much, and forwarding requirement is also too much. So TCP handles this problem in a more favorable way. You don't have to have the intermediate buffering or cache. Like, you're not caching, so the foreign agent doesn't need to cache, because TCP does not use split connection approach. This mobile TCP, this variant, which is called mobile TCP or MTCP, does not use split connection approach. Rather, it maintains end-to-end semantics. Then how does it work? Well, how does it take care of the wireless link, which can go out of coppers? Okay. Well, maybe I go this way. It has, this split connection approach type is split. Okay, two parts, but only for flow control. Remember that we had two different things. One was flow control, and the other was congestion. For flow control, it is still it uses that split connection approach to separate. But congestion control, the CWND, that window is maintained with end-to-end TCP semantic. It does not, in this case, it does not consider the separation of two parts, rather end-to-end. Meaning that whenever you have a packet lost, the retransmission has to occur from the sender. It has to come from there. So you don't need any buffering on the way. There is no buffering. So you get rid of that problem. But you see that it's somewhere in between. Flow control uses this split, so you solve the problem, to some good extent over there. And also those Snoop or ITCP came with some problem. That problem you handle gracefully. But in this case, now you maintain end-to-end semantics. Then the wireless link is taken care of this way. The BS monitor the X, and when it finds that the X are not received for a long period, okay, so it assumes that there is temporary disconnection. So it chokes the sender. It advertises back to the sender that the window size should be made 0. You don't need to send anything. So this is done by the intermediate network, the base station. It sends a window. It advertises a window. We know that there's a field in the TCP header to advertise how much should be sent. So it just puts that 0. And this is called persistent mode. So the sender will be in this state of persistent mode as long as the receiver is disconnected. Okay.
Sir,
can you
until
explain the persistent mode again?
well the see the when the BS always monitors what is happening here. When the BS realizes that there is a sudden wireless link disruption, data transfer is not possible for 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 some period. So it sends uh, to the sender a TCP header. I mean, we know that there is some TCP acknowledgement or some packets in the reverse direction, which includes advertised window, how much it should put in the link for transmission. In the advertised window, the BS puts 0. Don't send anything. So the sender does from then onwards does not send anything. It stops transmission. And this is called persistent mode of the sender. The sender will stay in this persistent mode. It keeps waiting until the BS again sends a positive number in the advertised window. So once a positive window advertisement is received, a value in the advertised window failed, then the sender exits the persistent mode and starts sending the packet. So it just turns off the transmission from the sending end. You see, here it is not buffering or anything. Just all the way to the sender, the BS sends a request that stop sending. And when the sender gets this message, it remembers the CWND, whatever condition window it had. It remembers that. And once it gets a positive advertised window field, it restarts or resumes its operation with the same CWND. The timeout period and condition window will be the same as it was before entering the persistent mode. Okay, so then you recover. So you had a sudden interference, you had a sudden shutdown in the link, but readily you can recover. Once you recover this link, your link quality may come back to the old quality, and TCP also starts sending with the same old condition window with the same data rate. So the data flow can be efficient while avoiding any buffering of any, it obviates the need for buffering packets in any intermediate node, which could be troublesome. Okay. However, there are also a few shortcomings with MTCP. You cannot achieve the full benefits of split connection approach. With the split connection approach, you had completely different links which you can configure, so you can take care of them separately. But here, for condition window, you have end-to-end semantics. So full benefit of the split connection cannot be achieved. So this is the problem when you have, say, high bit error rate. Okay, so some packets are lost because of high bit error rate, and and that can cause the advertised window to fall to 0. So, but it was because of, the packets come with different bit error rates. So this MTCP is fine as long as you have low bit error rate, but some high bit error rate can let the BS, the intermediate, think that okay, it is now the temporary disruption, so it may put the sender in persistent mode, although it shouldn't be the case. Just the bit rate has been little higher than normal, so that can be a problem. Okay, it can put the sender in persistent mode, which should not be the case then. Also, you need significant involvement of the base station. the base station is maintaining all this thing, advertisement of the window size. So it has to monitor and find out when there is a disruption in the wireless link, accordingly send the address window, then again send a positive address window to recover or to reinitiate the data transfer. So significant involvement of the base station is required. So this is pretty much completion of TCP. Just this TCP, I say that it is less important, but just one slide I have there. In the case of TCP, it is still uses the persistence mode and a temporary disconnection or temporary pause of data transfer. But here the mobile sends a message. Okay, it is not fully the involvement of the base station. Rather, you do it at the mobile level. When the mobile level keeps monitoring the signal strength, and based on the signal quality, since it's not wired, it's wireless, the signal quality can fall. So when it finds that, okay, the signal quality is now getting very poor, so I may get disconnected almost. It may be like out of coverage situation. So it sends a message that, okay, make it 0. Like instead of sending the advertisement window from the base station, it's from the mobile, this 0 window advertisement gets to the sender. Okay. Well, maybe okay. I revert from my comment that this is unimportant because recently I saw some papers working a lot with freeze TCP. Okay. So I think maybe freeze TCP is also now important. I mean, when I learned all these things, freeze TCP was not important. Okay, but nowadays it may be. So please ignore that comment. Consider all these 4 equally important. For mobile TCP is of course more important. Now, so the difference between mobile TCP and freeze TCP probably you now understand. But note that here, since it is from mobile network, it itself can go out of coverage. When it is from the base station can still send the mobile, even after the mobile network has gone out of coverage, the base station can send 0 advertisement window. But the mobile node cannot do. Once it goes out of coverage, it cannot communicate anyway. It cannot any longer send. So it has to do it once it feels that it's an impending disconnection. Okay, momentarily, I would get a disconnection. It is falling to almost 0. I'm going out of coverage. Right. So it says that okay, problem is going to occur. And the rest is pretty much the same. So it does not require that level of involvement of the base station. Okay. And it's better when you have in. Okay. Many people now use
Sir,
it.
we have another class from
Another class.
11:45.
Oh, okay. Oh, sorry. Once again, I could not follow the time. So I need to give everybody present today. And I need, of course, every extra class every week. These things I have added this year. Okay. Thank you for your time. If you have any questions, please raise them in the next class. And the seers, please schedule another class for me this week. Thank you so much.